Imagine balancing a plate on the tip of your finger. You instinctively search for its center point. This balancing point is like a centroid. In simple terms, the centroid is the average position of all the points in a shape. Think of a seesaw. Two people of equal weight will balance perfectly if they sit the same distance from the center. The center of the seesaw is its centroid. Now, imagine a triangle made of a thin, uniform material. The centroid of that triangle is the point where you could balance it perfectly on your fingertip. It's like the average location of all the triangle's points. This concept of finding the balance point extends to more complex shapes as well. We'll explore how to find these centroids in the next sections. Centroids are crucial in engineering and design. They help us understand how objects behave under different forces and loads. For example, when designing a bridge, engineers need to know where the weight of the bridge and any traffic will be concentrated. This is where the centroid comes in. By understanding the centroid, engineers can calculate the stresses and strains on the bridge structure. This ensures that the bridge is strong enough to support the load and won't collapse. Centroids are also important in fields like aerospace engineering, robotics, and even computer graphics. Finding the centroid of simple shapes can be quite intuitive. For a symmetrical shape like a square or a circle, the centroid is right in the middle. For more complex shapes, we use mathematical formulas. Don't worry, these formulas are like recipes for finding the centroid. They involve calculating the weighted average of all the points in the shape. For example, to find the centroid of a rectangle, we average the x-coordinates and the y-coordinates of its four corners. Each shape has its own formula, but the principle remains the same. Find the average position of all points. Imagine spinning a bicycle wheel. Now imagine trying to spin a massive merry-go-round. Which one is harder to get spinning? The merry-go-round, of course. This resistance to changes in rotation is due to its moment of inertia. Moment of inertia is like an object's resistance to being spun or twisted. The heavier and farther the mass is from the axis of rotation, the greater the moment of inertia. Think of it like this. It's easier to push open a door by the handle than by pushing near the hinges. The farther your push is from the hinges, the axis of rotation, the greater the moment of inertia, and the harder you have to push. Section 5. Spinning right round moment of inertia in action. Moment of inertia is crucial in many aspects of engineering and physics. It determines how easily an object can be rotated, which is essential for designing things that spin or resist spinning. For instance, a figure skater spins faster when they pull their arms in. This is because they're decreasing their moment of inertia. Similarly, flywheels used for energy storage are designed with high moments of inertia to resist changes in their rotational speed, allowing them to store energy efficiently. Section 6. Calculating the spin doctor, moment of inertia for simple shapes. Just like with centroids, there are formulas to calculate the moment of inertia for basic shapes. These formulas consider the shape's mass and how that mass is distributed relative to the axis of rotation. For example, the moment of inertia of a thin rod rotating about its end is different from that of a solid cylinder rotating about its central axis, even if they have the same mass. These formulas might seem intimidating, but they are essentially tools to quantify an object's resistance to changes in its rotation, which is crucial for many engineering applications. Section 7. From seesaws to spaceships, real-world applications. Centroids and moments of inertia are everywhere in our daily lives and in advanced technology. We've already mentioned bridges and figure skaters, but the applications go far beyond. From designing stable furniture to optimizing the performance of airplanes and spacecraft, these concepts are essential. Understanding centroids helps us build structures that won't tip over, while understanding moment of inertia helps us design vehicles that are fuel-efficient and maneuverable. Section 8. Conclusion. The power of the center and the spin. Centroids and moments of inertia, though they might sound like complex engineering jargon, are actually fundamental concepts that govern how objects behave in the physical world. Understanding the center of gravity and an object's resistance to rotation is essential for designing safe, efficient, and functional structures, machines, and vehicles. So, the next time you see a spinning object or a stable structure, remember the power of the center and the spin.